It's one of those we got to do it because we got to do it kind of situations, you know? My fault. Let me just like get this little box out over here. We should be good to go. All right, so what we about to talk about right now has already been posted, so y'all could like knock that out when y'all get a chance. What we're gonna finish talking about later tonight. I didn't post that homework yet. I'm gonna post it as soon as I can. All right. This will be on test two, what we're doing right now. All right. It's gonna be good. Um, this is gonna be something. I don't know. I don't know. I'm not a fan of this, but we gonna go through it, right? Go ahead. So
From the that
yeah,
it didn't like that.
no, it's not commutative. So like whatever we did, what's that day before Thursday? Wednesday? So whatever we did Wednesday and then today, a little bit of tomorrow, that's gonna be exam two. Yeah. It's not gonna be as big as exam one. Yeah. But it'll be doable. It'll be doable. Yeah. All right, let's look at this, right? So the exterior of the Lincoln Memorial in Washington, D.C. is a large rectangular solid with length 61.5 meters. Wow. With a has a width of 40 meters and a height of 30 meters, right? We can easily find the volume using elementary geometry, right? So, volume is equal to length times width times height, right? So 61.5 times 40 times 30, little calculator, boop, 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 we get 73,800, right? So the volume is 73,800 cubic meters, right? Suppose we know the volume, the length, and the width, but we could divide to find the height, right? So we know how to do this, right? Solve for another variable, right? So the height is equal to the volume divided by the length times the width. Plug in the numbers, bop, 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 get 30. All right. So as we can confirm, conform, right, from the dimensions above, the height is 30 meters, right? So we can use similar methods to find any of the missing dimensions. We can also use the same method if any or all of the measurements contain variable expressions. For example, suppose the volume of the rectangular solid is given by the polynomial 3x to the fourth power minus 3x cubed minus 33x squared plus 54x. The length of the solid is given by 3x. The width is given by x minus 2. To find the height of the solid, we can use polynomial division, which is our focus for this section, right? So we're going to be dividing polynomials. Yay. All right. Now I realize some of y'all probably even know how to do this from 28. If that's the case, knock out your homework, right? If not, check it out. This is going to be a real quick lesson. I'm sure all of you know how to do this already. All right. So here we go, right? We're going to be using long division to divide polynomials. All right. So we're familiar with the long division algorithm for ordinary arithmetic. We've all seen this, right? We begin by dividing into the digits of the dividend that have the greatest place value. We divide, multiply, subtract, include a digit in the next place value position, and repeat. For example, let's divide 178 by 3, right? Using long division, right? We already know this, right? 3 goes into 17, right? 5 times. And then 3 times 5 is going to give us our 15 right here, right? Then we want to subtract that, which gives us our 2. Bring down the 8. Can't forget to bring down that 8. Now 28. 3 goes into 28. 9 times 3, we know is 27, right? With the remainder of 1. Nothing new here, right? Basic. And then another way to look at the solution is as a sum of parts, right? So I'm taking it up a notch now, right? So this looks familiar since this is the same method used to check division in elementary arithmetic. So the dividend, right, is equal to the divisor times the quotient plus the remainder, right? So just to recap, right? Dividend, right, is going to be this inside number here, the 178. Divisor, what am I dividing it by? The 3. The quotient, right, is going to be our answer. And the remainder is this thing at the end, what's left over, right? Okay. And then, of course, you just plug in the numbers, bop, 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 and it works, right? So we call this the division algorithm, right? And we will discuss it more formally after looking at an example. Go ahead. You're welcome. So check this out. I'm gonna be honest with y'all. This is my favorite method right here for dividing polynomials, right? Long division. I love this method, right? I am going to show you another method tonight that you can use. I hate that method. I got to go through it. All right. Synthetic, yeah. Way more. Yeah, yeah. I'm gonna tell you the reason why, matter of fact, right? I'll break and tell you. So when you're doing synthetic, right, you need to have a root, right? You can only do synthetic with one root. But with long division, see, I had 3 roots. And say it was like to the 8th power or something like that, right? By me having 3 roots, I could combine them 3 roots into a polynomial. And then I could divide that massive polynomial by the even bigger polynomial and get it even smaller, you know? But I can't do that with synthetic. Synthetic, I gotta try every single damn root till I find it. Like, nah. This saves way more time, man. All right. So division of polynomials that contain more than one term has similarities to long division of whole numbers. We can write a polynomial dividend as the product of the divisor and the quotient added to the remainder. The terms of the polynomial division correspond to the digits and place values of the whole number division. This method allows us to divide 2 polynomials. So for example, if we were to divide 2x cubed minus 3x squared plus 4x plus 5 by x plus 2 using long division algorithm, this is what it would look like, right? So we have the x plus 2 here. We're dividing it. Well, no. We have the 2x cubed minus 3x squared plus 4x plus 5. We're dividing it by x plus 2. So we set it up, right? Let's see how we want to do this now. I can. Is this good? Or more? Good. All right. So we have it set up here, right? Let's go through the motions with this real quick, right? I have x plus 2, right? And I want to divide it in, right? So x goes into 2x cubed how many times? 2x squared, right? So that's why I write my 2x squared up here, right? After that, I multiply 2x squared by x, and that's going to give me 2x cubed. Then I multiply 2x squared by 2, and that's going to give me the 4x squared. After that, you subtract, right? Now, this is polynomial subtraction, right? So remember that this is going to get distributed over here, and then you add, right? So 2x cubed minus 2x cubed, you already know, right? Negative 3x squared minus 4x squared is negative 7x squared, right? Then what do? Bring down the next one. Bring it down. So now I have negative 7x squared plus 4x. X goes into negative 7x squared, negative 7x times, right? So now what am I gonna do? Negative 7x times x is gonna give me a negative 7x squared right here, right? Then I'm going to take my negative 7x, multiply that by 2. That gives me my negative 14x right here, right? After that, what do? Subtract. Negative 7x squared minus negative 7x squared, you already know. It cancels out, right? Now, check this out. 4x minus negative 14x, a negative times a negative is a positive, right? So 4 plus 14, that's my 18x right here. Bring down the last number, that 5. Now, x goes into 18x positive 18 times, right? So now 18 times x, that's going to give me my 18x right here. And then now 18 times 2, that's my 36 right here. Subtract. You already know 18x minus 18x, that's gone, right? 5 minus 36, negative 31, right? So boom. So here's what we got. We have our quotient on top. Let me erase all the writing so you can see it, right? So my quotient, I have 2x squared minus 7x plus 18 minus, right? It's minus because of the negative in front of the 31. 31 on top, and then my divisor on the bottom, right? It's my favorite right here. That's the long division. That's it. That's it. Mm-hmm.
That's crazy.
Yep. 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 Mm-hmm. Not really. Just dividing it. Yeah. The idea is there. Yeah. It's just that it's more detailed in the way that we divide it, you know? So said a little differently, right? We have 2x cubed minus 3x squared plus 4x plus 5. We could also rewrite this as x plus 2 times 2x squared minus 7x plus 18 minus 31, right? So we can identify the dividend, right, as the 2x cubed minus 3x squared plus 4x plus 5. The divisor is x plus 2. The quotient, right, is 2x squared minus 7x plus 18. And our remainder is the negative 31, right? So this is our division algorithm, right?
5 by x multiplied by 2, that's correct.
Yeah. Mhm. I'm kind of showing y'all this, like, so that you could see how it's done. But in actuality, like on the test and stuff, I'm just gonna give you two polynomials and you just divide them and just give me the quotient and I'm good with that. Right? If there's no remainder. If there's a remainder, then I want to see like the remainder divided by the divisor, all of that stuff. You know? A mixed number. I want to see a mixed number. That's what it is. It's a mixed number. Well, it's really a mixed polynomial, but y'all get what I mean. You get what I mean. All right. Just to recap the division algorithm. All right. So the division algorithm states that given a polynomial dividend f of x and a non-zero polynomial divisor d of x, where the degree of d of x is less than or equal to the degree of f of x, there exists unique polynomials q of x and r of x such that f of x is equal to the d of x times q of x plus r of x, right? D of x is dividend, right? Q of x quotient, R of x remainder. All right. So Q of x quotient, R of x remainder. The remainder is either equal to 0 or has degree strictly less than D of x. If R of x is equal to 0, then D of x divides evenly into F of x. This means that in this case, both D of x and Q of x are factors of F of x. All right. A little complex, but I promise you, in doing, you guys know what this is.
Yeah, like, formula.
Yeah, yeah. Let me give y'all a little bit of tea real quick before we jump into an example. Uh-huh. You mean P over Q? You mean P over Q? I feel like what you're asking, we're gonna get to in a little bit. Yeah. I got you. All right, let me just give you a little bit of tea real quick before we jump into a example, right? So given a polynomial and a binomial, we're gonna use long division to divide the polynomial by the binomial. All right. So first things first, you want to set up the division problem, right? So the denominator, divisor, whatever, that goes on the outside, dividend on the inside, right? Determine the first, excuse me, determine the first term of the quotient by dividing the leading term of the dividend by the leading term of the divisor. Step 3, multiply the answer by the divisor and write it below, right, the like terms of the dividend, right? Step 4, subtract the bottom binomial by the top binomial. Step 5, bring down the next term of the dividend. Step 6, repeat steps 2 through 5 until you reach the last term of the dividend. Step 7, if the remainder is not 0, express the fraction using the divisor as the denominator. Right? We know this already. This is how you do long division with numbers. It's the same thing, but now we're doing it with polynomials. Literally the same process, the same everything. All right? Uh-huh.
How do you get the from
The device is given to you in a question. Yeah.
What if they just give you a polynomial, so to figure out the bottom?
We get into that. Get into that, yeah. So all right, let's try this out. Not too complicated, right? I got 5x squared plus 3x minus 2, and I want to divide that by x plus 1, right? Just want to show y'all something. This could also be written as something like this: 5x squared plus 3x minus 2 over x plus 1. It means the same thing. I just want to show y'all that it could be written as that as well. Y'all probably know that already, so all right. So anyway, right? Let's set it up. X plus 1. And this is the 5x squared plus 3x minus 2, right? Real nice and simple. X goes into 5x squared how many times? 5 what? 5x, right? Now 5x times x is what? 5x squared, right? Now 5x times 1 is what? It's 5x, right? So plus 5x. This is a polynomial, so we're going to subtract, right? So 5x squared minus 5x squared is 0, right? That just cancels out. Let me change my color for that because that's important. Goodbye, right? No, because you're subtracting the same thing. Like 3 minus 3. Yeah.
5x squared. But we stick with trying to keep them in similar formats.
Same format. Yeah, same format, right? Go back up.
Not like, you get the five, it's,
So I took the 5x, I multiplied it times x, and that's how I got the 5x squared, right? Then I took the 5x and I multiplied it by 1, and then that's how I got the 5x right here, you know? Same division. Mhm.
so it's five,
Mm-hmm.
five times. Yeah.
X goes into 5x squared 5x times. The whole thing.
That's what we got.
Yeah. 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 And then now let's do our subtraction, right? Last one. 3x minus 5x equals no, negative 2x, right? And then you want to bring down the next one, negative 2. Now, x goes into negative 2x how many times? Close. No. X goes into negative 2x how many times? Not once. Close. You're close. No. Almost there. Negative 2. Now we're talking, right? Negative 2, right? So now negative 2 times x is what? Negative 2x. And negative 2 times 1 is what? Negative 2, right? Remember, this is polynomial, right? So I want to put in parentheses, subtract this, right? Now, negative 2x minus negative 2x is what? 0, right? That cancels out. Negative 2 minus negative 2 is what? 0, right? Boom, remainder 0. So what's my answer? 5x minus 2. Box it, you're done. Questions on this, anybody?
Where five times, right?
5x times.
Yeah,
Yeah. Because I need another x to make x squared.
and then we take that x,
Mm-hmm.
x goes to five x squared, five x times,
Right.
and then we multiply that by the divisor.
Mm-hmm.
That's what we're subtracting from the polynomial.
Exactly. Okay. They just bring down the next one and so forth.
And negative, so negative, x goes to negative 2x.
Okay.
2 times because it's only an x there, right?
Negative 2 times.
Yeah, negative.
Right.
I got that like negative squared, and we're gonna play it to 2x squared, 2 times, 2x times.
It would have been negative 2x,
Yeah.
right? Because I needed one more x to make x squared. Yeah. Multiply with not gonna lie, this is pretty much enough information for y'all to just knock out the homework, but let's keep going. Huh? Oh yeah, we could do more. Oh, it's coming.
Yeah.
It's coming. But the thing is that the process doesn't change though. Yeah. Yeah. It's just that the process doesn't change. It's the same thing again and again, right? So just a little analysis real quick. The division problem had a remainder of 0. This tells us that the dividend is divided evenly by the divisor, right? And that the divisor is a factor of the dividend. Just pointing out the obvious. All right, just pointing out the obvious. All right. Just because y'all asked for another example. Even though this has more coefficients in them, and the coefficient is not 1, blah, 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 it's the same process. Doesn't change. All right? Same thing. Y'all want a minute to try it, or should I just jump into it? You try it? I don't know. Mhm. Really? It's the easy part. It's not. Oh man. Pretty sure this is on the formula sheet too. Let's see how this weather is looking.
No.
I mean, to be honest with you, from my angle, with the light, I can't see like the reflection of the light. Damn, man, out of luck. This joint say 11 o'clock tonight it stops. Oh man. Y'all want to do a study session till 11 tonight? Right? Oh man. Now we could probably chance something like 9 o'clock is not like perfect, but it'll be all right. Yeah, definitely 11 o'clock. 10 o'clock is probably dying. Woo! You live in Jersey, vaya con Dios. Um, they got a whole flood over there. I hope it's not like Texas. Like Texas on some next level joint with they flood. Yeah. But you know what I don't like though? Like people who know how to like develop houses and stuff, right? Y'all clearly know that it's a flood zone, right? Even though it happens once every 100 years or whatever, but it happens, right? Why y'all still build houses there? Like the developer people, I'm saying, like y'all know what it is. Y'all still building houses there, like insurance.
You know, that
Mhm.
insurance. And you get insurance for it, if I'm not even, floods, like once every 25 years, Whatever they were in.
Damn.
And then plus the year that you.
And then they.
That's another thing. Yeah. It's terrible, man. No.
So that's, I mean, that's.
Yeah.
It shows it's such a scam.
Mhm.
Like,
Some of it is, yeah.
the fact that we don't, I'll tell you, it's crazy.
Mm.
Like if I was driving, I get like the drive, like this, like that, you
Mhm.
know, I like to that happen, because then I have to drive y'all.
Yeah.
But I would much rather put my money in like a government saving mortgage. And put the money in there, because how you charging me, supposed to protect me, and now something's happening to me, and I charge me more. Keep me alive. And
True.
I'm forced, it's illegal for me not to pay, it's crazy.
It's true.
That's illegal for me not to pay.
That's because they lobby mad hard, you know, but their lobby is real. Yeah. Yeah. Nah, you know which insurance is the biggest scam though? Whole life insurance.
Yeah.
Nah, whole life is term life is okay. But whole life, like nah. Yo, that's a scam and a half right there. Yeah.
I would get a house. I get a
But-
book with my insurance, and I don't pay the principal and interest. to myself.
But peep this though, right? Like, say you want to take out a loan from your
Yeah,
thing, right? You got to pay that back with interest.
yeah,
It's your money.
yeah. But you gotta think about it, you're not, the bond will pay interest.
Yeah.
So,
But it's not to you though. And you know what's funny? When you pass away, your beneficiary gets the payout amount,
Yeah.
not the interest,
not the interest.
not the money that you is. So it's
See, but that's why they didn't take that. So much policy, make sure it's like, reputable stuff that it's trust. And then.
but it can't go into a trust. That's the issue. That's the issue, you know? All right, let's look at this real quick. Y'all finished it? It was easy, right?
Yeah.
Alright. Let's
I don't.
look. 3x minus 2 into the 6x cubed plus 11x minus 31x plus 15. You know what? I forgot the x squared. All right, boom. Let's do it. 3x goes into 6x cubed how many times?
X, 2x.
2x squared. Very good. Right? So now 2x squared, you know what? I should do this in colors. Let me do this in colors. I'm gonna just go through the whole spectrum. I'm gonna go through the whole spectrum. Let's start off with orange, right? So this is 2x squared, right? So 2x squared times 3x is what? 6x cubed. And then 2x squared times negative 2, negative 4x squared. Perfect, 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 right? Remember, this is a polynomial, so I'm going to subtract, right? Now, 6x cubed minus 6x cubed is 0, right? So that's gone, right? 11x squared minus 4x squared. What's that?
15x.
15x squared. That's perfect, right? All right. And then next, you got to bring that down, right? Negative 31x. Yep, bring that down. Let's go to the next color. All right. Now, 3x goes into 15x squared. How many times?
X.
Plus 5x. All right. Now, 5x times 3x is 15x squared. Now, 5x times negative 2, negative 10x. Very good, right? Now, remember, this is polynomial, so gotta subtract. Now, 15x squared minus 15x squared cancels out. Now, negative 31x minus negative 10x. Negative 21x. Perfect. Then we want to bring down that that positive 15, excuse me, right? Now, 3x goes into negative 21x how many times? Negative 7. Good, good, good. Hold on, I need another color. Negative 7, right? Now, negative 7 times 3x, that's going to be and negative 7 times negative 2, positive 14, right? So now I just want to subtract this. Remember this polynomial. So negative 21x minus negative 21x. 0. Very good. Now 15 minus 14. Perfect, perfect, right? So what's my answer? Right? Couple ways we could do this. I like this way. 2x squared. I like the mixed number way. Plus 5x minus 7. Remainder on top. So plus remainder on top 1 over the divisor. 3x minus 2. All right. And that's it. Questions on that? Go ahead. The 15x squared. Perfect, right? So right here, the first one, right? The black one, the 15x black one. Okay. So that's 11x squared minus negative 4x squared, right? So think of it as 11 minus negative 4. Negative, negative is positive. So 11 plus 4, 15. No, it's positive 15x squared. The black one, right? Or the purple one, you mean? 11 minus negative 4. Yeah, because it's 2x squared times negative 2, right? Yeah.
I keep getting to.
Yeah. Got you.
That's kind of what we do, we got that's 7,
Right. And then adding, right? That's it. That's it.
What if like, people wanted to say we got this, so I have an x squared left over. If that was the case, in the middle of a polynomial, we already have to make it. If we just continue on from there and then carry that
Yeah.
into the remaining section.
Keep going until you can't go anymore. Like we reached the end of this, so that's why we can't do anymore. So we just have the remainder divided by the divisor, and that's it. You know, like a mixed number.
That's what I was like this. The problem is, but I don't know.
Yeah.
You can't like, you know how like, oh, like I said, like. It was like a regular long division.
Yeah.
And how we could pull for the second, put it to this.
Hmm.
I don't know how I would do that with a polynomial.
Like you mean you would factor it and find like a factor?
Kind of
Like what? See, yeah, like a number or something.
yeah, so this one, I had this as a remainder, and I pretty much kept going till I got to the problem and then put it all over 3x minus 2.
It's the same problem we were doing.
Yeah, but I forgot to distribute the negative side down back.
Let's see, here's the first one though, right? 11 minus negative 4.
Yeah.
15x squared. So that was the only thing.
What would I do with that? I forgot to remember. Like, you know, like say I was doing like long division 11, 5 divided by 1, that goes to that twice, 10 minus, and now I have 11. So then I could just repeat the same thing and I'll have a remainder over.
Exactly. So 5 goes into 11.
Is it
2
possible
times.
to do this with the polynomial? So
No.
let's say this was like 1x and then this point.
Even with this, it's not right because 5 can still go into it. It's when 5 can't go into it, like when it's like just the 1 by itself, then that's when you stop. Yeah. It's like same thing with here, right? So we were good right here, but then when we got to the 1, 3x can't go into 1, so that's how I know to stop.
So that automatically becomes a remainder, okay? Because I'm like, sometimes it'd be like, oh, so like this is like 1, for example, like 1x plus, you know, 2x.
Yeah.
I wouldn't be able to pull the 2x down into it and combine them and all this stuff.
You would, because it's not the end. Yeah, when you get to the last one, that's when it's like, we're done, we can't go any further. Yeah.
I'm like, these seem like perfect waffles, so I what if I didn't have a perfect waffle?
Nah, this a complicated one right here.
Yeah.
Yeah. Just want to give you guys a little analysis before we move on. So we can check our work by using the division algorithm and rewrite the solution, right? So we can rewrite this as 3x minus 2 times 2x squared plus 5x minus 7 plus 1. This gives us back out the original. So the dividend is the 6x cubed plus 11x squared minus 31x plus 15. The divisor is a 3x minus 2. The quotient is the 2x squared plus 5x minus 7. And the remainder is 1. Okay. Good times. Y'all want to try another one? It's the same question. I'm just labeling it all. That's all. Yeah. But there isn't though. In this, yeah. See, you have 6, 11, 31, 15. There's nothing common all of them. But yes, always if there's a polynomial right there, the first thought is the GCF before we go in and do anything else. Yeah. I'll let you guys try another one. A little bit harder. A little bit harder. If you're bored, you can knock out your homework. I get it. Y'all good? All right, let's try this. All right. A little bit harder. All right, so we got 4x plus 5. See, I can't draw. I'm trying though, I'm trying. 16x cubed minus 12x squared plus 20x minus 3, right? Okay, so 4x goes into 16x cubed how many times? Perfect. 4x squared times 4x is cubed. Now, 4x squared times 5, what's that? Plus 20x squared. Perfect. Now, remember, this is polynomial, so we're going to subtract. 16x cubed minus 16x cubed is 0. This cancels out. Negative 12x squared minus 20x squared. What's that? Perfect. Now we want to bring down the next one. This is plus 20x. Now 4x goes into negative 32x squared. How many times?
Negative 8x.
Negative 8x. That sounds good. Let me show you. 8, 8, 60, 30. You're good. Now negative 8x times 4. Negative
X.
32x squared. Negative 8x times 5.
Negative 40x.
Negative 40x. And then I want to subtract this. Negative 32x squared minus 32x squared is 0. 20x minus negative 40x. What's that?
60x.
60x.
60.
Good. Mm-hmm. And minus 3, yep. Because negative and negative is positive. 20 minus, yeah. Now 4x goes into 60x how many times?
15x.
Okay, so plus 15. 15 times 4 is 60, right? And then 15 times 5 is 25.
5. 25. 75.
30,
75.
60, 70, 75, right? And then we want to subtract this, right? Okay. So now 60x minus 60x, negative 3 minus 75.
Negative 78.
Negative 78. All right. So maybe we do 4x squared minus 8x plus 15 plus negative 78. Right? Over the divisor, which is 4x plus 5. That's it. Questions on this, anybody? Sure. So that one was the 15 up here, 15 times the 4x. And then 15 times the positive 5. The positive 5 to get the 75. And then you just subtract it. Hmm? All right. Let's get into my least favorite part. Here we go. So we're going to be using synthetic division to divide polynomials, right? So as we've seen, long division of polynomials can involve many steps and be quite cumbersome, right? Synthetic division is a shorthand method of dividing polynomials for the special case of dividing by a linear factor whose leading coefficient is what? So to illustrate the process, recall the example at the beginning of the session, 2x cubed minus 3x squared plus 4x plus 5, right? We're going to divide that by x plus 2. Using the long division algorithm, right? The final form was 2x squared minus 7x plus 18 with the remainder of negative 31. So there's a lot of repetition in the table if we don't write the variables, but instead line up the coefficients in columns under the division sign and also eliminate the partial products. We already have a similar version of this entire problem, right? So 2 divided by 2, negative 3, 4, 5, right? So synthetic division carries a simplification even a few more steps. Collapse the table by moving each of the rows up to fulfill any vacant spots. Also include, also instead of dividing by 2, whereas we would have as we would in division of whole numbers, then multiplying and subtracting the middle product, we change the sign to the divisor to -2, multiply and add. So -2 times 2, right? Times the -3 times 4 times 5. So -2 times 2 is going to bring down 2. -2, right? Times the 2 on the bottom, that's 4. That's going to give you the -4 right here. Add them up. -3 plus -4, that's -7. All right? And then the -2 times -7 gives me a -14, right? And then you want to do 4, right? Plus the 14 to get you 18. Now, -2 goes into 18, right? That should be, wait. -2 times 18 is going to give you -36. Then you just add straight down, and you get the -31. -31, once again, is my remainder, right? If it was 0, then we could say that it was fully divisible, like I said, a factor. But because it's a remainder of 31, it's not. So we multiply it by the divisor and add the repeating process column by column until there's no entries left. The bottom row represents the coefficient of the quotient, and the last of the bottom row is the remainder. In this case, the quotient is 2x squared minus 7x plus 18, and the remainder is 31. And we're gonna see an example of this.
When it was there, they pull up the x squared, the x cubed.
Uh-huh.
All of this, put it back.
Exactly. We'll just use those coefficients to do it.
Yeah. That's about the same.
I still like the other way better. Right? So synthetic division is a shortcut that can be used when a divisor is a binomial of the form x minus k. In synthetic division, only the coefficients are used in the division process. All right? Nope. This method sucks. You guys try.
You said you could. Vision.
I can multiply multiple roots together, to get a big polynomial and then divide it by a bigger polynomial. I can't do that with synthetic division. I have to know all the zeros and I have to try all of them. It sucks. Try it out, try it out, try it out. So do we do it? All right. Let's look at this now. X minus 3 equals 0. Add 3 over here. Add 3 over here. X equals 3. 3 will be your number on the outside. The numbers that we're going to write inside here will be the coefficients, the numbers in front of the variables. So for x squared, I have 5. And I have negative 3. And I have negative 36. Did I write this right? I believe I did. Maybe that should have been a little bit further down, something like that, right? So first things first, bring down 5. Now, 3 times 5 is 15, right? Excuse me. Then we want to add these together. 12. 3 times 12 is 36, right? And then negative 3 times 36 is, excuse me, negative 3 plus 36, excuse me, is 33. All right? No, just 33. Yeah. The 5 was given to me. Huh? That's supposed to be 36, isn't it? Wow. Thank you. Oops. Thank you. Appreciate that. So 0, right? So what's my divisor, right? Quotient, I meant to say. What's my quotient, right? So my quotient is 5x plus 12. All right? So when I divide this out, the x minus 3 and the 5x squared minus 3x minus 36, one factor is 5x plus 12. I still hate this method. It was given 5x squared. That's the coefficient of x squared. You just bring it down. That's always step 1. Bring that down. And then 3 times 5, 15. And then you add them together. Negative 3 plus 15, 12.
So we times 5, that's subtract that from the next.
Add it. Negative 3 plus 15 is 12. Right. Then now 3 times 12, 36. Then you add it. Negative 36 plus 36, 0. So that last number you got is always going to be your remainder.
Show me what's
Yeah. Yes. Say it again. The answer is 5x plus 12. And it comes from this. Yeah. With remainder 0. So this would be the remainder. Yeah. So your first step is always to bring down the leading coefficient, whatever that is. Which 36? The positive 36 is 3 times 12. 3 times 12. Yeah. Gives you 36. Yeah. All right. So first you always bring down the leading coefficient. Then you multiply whatever the divisor is by that number. So 3 times 5, right? 3 times 5, that gives me the 15. After you have the 15 there circled, you add. So negative 3 plus 15 is 12, right? Then, after that, 3 times 12, that gives you the positive 36. Now you can add again, and you get 0. So 5x plus 12. All right? By the way, I'm not gonna like point at y'all and be like, yo, give me this answer in synthetic division. Give it to me in long. Just give me the answer. I don't care. What work does that? But you could just write down the right answer. Yeah. Yeah. Even though it's saying it, you could just write down the right answer. You know, like using long division if you want. Yeah. No. Just give me the answer and I'm happy. You know? Real quick, just to give you a special note. So just as with long division, we can check our work by multiplying the quotient by the divisor and adding the remainder. So x minus 3 times the 5x plus 12 plus 0 gives us back the original equation we had, 5x squared minus 3x minus 36. All right? You guys try. So we good? All right, let's go through it. Not my favorite. So I got x plus 2 is equal to 0. I'm gonna subtract 2. I do the one side, do to the other, blah, blah, blah. So now I have x equals -2. All right, so that's gonna be my number on the outside, -2. And let's just write down the coefficients of the polynomial here. So I have 4. Huh? Yeah, yeah. Software. So 4, 10, -6, -20, right? First things first, bring down the first term. Now, -2 times 4 is -8. Now, 10 plus -8 is, no, 10 plus -8, 2, right? Now, -2 times 2 is -4. Now, -6 plus -4 is -10. Now, -2 times -10 is +20, right? And then -20 plus 20 is perfect. So what's my quotient divisor, whatever? It's gonna be x to the, oh, actually, wait, no. It's 4x what?
Where?
Squared, keep going,
Close to X.
plus 2x minus 10. Perfect. And that's it. Huh? That was the original, but when I divided out one of the x's becomes to the second. Yeah. Everybody got this answer? No. Not my favorite, but if y'all want to use it, go ahead and use it.
Way down the vertical multiply by Add the answer
Right,
in the space of the next coefficient,
right.
and then
Yeah.
divide,
And just add and do it over. So you can't do it no more. Hmm? That's fine. So the graph of the polynomial 4x³ plus 10x² minus 6x minus 20 in this figure shows a 0 at x equals k equals -2, right? So this confirms that x plus 2 is a factor of 4x³ plus 10x² plus, oh, excuse me, minus 6x minus 20. That's it. Let me ask y'all a question. Y'all get it or y'all want to see another example? Got it? Got it? Huh?
divide.
Yeah.
Wow.
Mhm.
Alright. If you place an X, and there's no Y axis, and how far it takes it to get to it, you go to. But this one is X plus 2.
That one is it, we're just picking a
What?
polynomial to divide it by, and then we divide it. And we see what happens. No? Y'all need to see another one or y'all good? Ooh, I saw that. I was like, one more or we can move on. What we say? We move on?
This is in, this is,
I'm sorry?
static number.
Yeah. I mean, my next example is gonna be if there was a remainder. But y'all could probably guess what's gonna happen. Do y'all want to see a remainder or no?
No,
Yeah. But what happened in the remainder is that you see right here where this is 0, right? That's gonna be a number. And if that's a number, you know you're gonna have the original answer here with the remainder divided by the divisor. And that's all it is. You wanna see it? All right.
And if X will be able to stop there, because it's not good for.
Exactly. Huh? The graph? It's just showing you where the zeros is. You know? I was bouncing off. It's okay. That was something from another class. All right, last example, then we're gonna move on. So using synthetic division to divide a 4th degree polynomial, right? So we have -9 x to the 4th plus 10x to the cube, excuse me, plus 7x² minus 6 by x minus 1. All right. So let's start it off. X minus 1 equals 0. I'm gonna add 1. When I do to one side, do to the other, so x is equal to 1. So 1 is gonna be my divisor. Write down the coefficients. I have negative 9, 10, 7, negative 6. Okay. Start first, bring this down. I have negative 9. Now, 1 times negative 9 is negative 9. I'm going to add it. 10 plus negative 9 is 1. Okay, 1 times 1 is 1. Now, 7 plus 1 is 8. Now, 1 times 8 is 8. Now, negative 6 plus 8 is 2. So now here's my answer, right? This is going to be negative 9 x cubed.
Plus, x squared,
Uh-huh.
plus 8x. Plus,
Not plus 2.
plus
Plus 2 over x minus 1.
push up.
Mm-hmm. Unfortunately. You know what? I feel like we missed something here. What did I miss? Oh, you know what I did? Hold on. Let's do this again. Hold on. I made a mistake. I made a mistake. It's that yeah. It's that time of the night. That's all that is. It's all that time of the night. All right, anyway, let's try that again. 1 is still there though. 1 was right. So negative 9x to the fourth, 10x to the third, 7x squared, 0x, and then now negative 6. That's better. Right. Now it'll work out, right? So we want to bring down the negative 9. Now, 1 times negative 9 is negative 9. Now, 10 plus negative 9 is 1. 1 times 1 is 1. All right. Now, 7 plus 1 is 8. Good. Now, 1 times 8 is 8. Now, 0 plus 8 is 8. Now, 1 times 8 is 8. So then now, negative 6 plus 8 is 2, right? Now we got it. So now this is negative 9x cubed plus x squared plus 8x plus 8 plus 2 over x minus 2. That's it. X minus 1. Sorry about that. X minus 1. Apologize. Questions on this?
You know, the spot next to be out there.
Right. Yeah. That if we don't do it, it throws off the whole problem.
About like 4x
Yeah.
plus 1. Call it 9 6.
Mm-hmm. Yeah.
And the problem not that's busting myself that we. But the coefficient, you start off with x minus 1.
For synthetic division, yes. For long division, no.
Again,
Yeah. All right. So we good? All right. Enjoy the homework. Let's move on. So a new bakery offers decorated multi-tiered cakes for display and cutting at quinceañeras and wedding celebrations, as well as sheet cakes to serve most of the guests. The bakery wants the volume of the small sheet cake to be 351 cubic inches. The cake is in the shape of a rectangular solid. They want the length of the cake to be 4 inches longer than the width of the cake and the height of the cake to be 1/3 that of the width. What should the dimensions of the cake pan be? All right. So this problem can be solved by writing a cubic function and solving a cubic equation for the volume of the cake. In this section, we will discuss a variety of tools for writing polynomial functions and solving polynomial functions. All right. It's going to be interesting now. So evaluating a polynomial using the remainder theorem. So in the last section, we learned how to divide polynomials. We can now use polynomial division to evaluate polynomials using the remainder theorem. So that is if the polynomial is divided by x minus k, right? The remainder may be found quickly by evaluating the polynomial function at k, that is f of k. Let's walk through the proof of the theorem. Recall that the division algorithm states that given a polynomial dividend, f of x, and a non-zero polynomial divisor, d of x, where the degree of d of x is less than or equal to the degree of f of x, there exist unique polynomials q of x and r of x such that f of x equals d of x, q of x plus r of x. If the divisor d of x is MIA or whatever, x minus k, this takes the form f of x is equal to, open parentheses, x minus k times q of x plus r. Since the divisor x minus k is linear, the remainder will be a constraint, r. Also, if we celebrated for this x equals k, we have f of k is equal to k minus k, q of x plus r, where 0 plus the q of x plus r. In other words, f of k is the remainder obtained by dividing f of x by x minus k. Okay. Yippee-doo. I'm getting to it. It's a lot simpler than it might look. The remainder theorem, if a polynomial f of x is divided by x minus k, then the remainder is the value f of k, right? We already know this. We did this already. All right, so given a polynomial function f, we want to evaluate f of x is equal to x equal to k using the remainder theorem. So first you want to use the synthetic division to divide the polynomial x minus k. And two, the remainder is the value of f of k. That's simple. Try it out. Question here is, what is the remainder? Please and thank you. Use synthetic division, just find the remainder. That's all I'm asking here. Use long division if you want, find the remainder. So we got it? All right, let's take a look. Now I'm only using synthetic division because they told me to. But if it was me on the test, I'd use long division. Anyway, let's do it. 2. I was just checking right here to make sure that I said x equals, right? So 2, I have 6x to the 4th power, negative 1x cubed, negative 15x squared, positive 2x minus 7. Bring down the first term, right? So now 2 times 6 is 12, right? Now, negative 1 plus 12 is 11. Now, 2 times 11 is 22. Now, negative 15 plus 22 is what? It's 5, 6, 7. Good. Now, 2 times 7 is 14, right? Now, 2 plus 14 is 16, and 2 times 16 is 32, and then -7 plus 32 is what? 25. So real quick, my remainder, I'm so used to math, is 25. All right? Okay? Just want to make a special note real quick. I don't know if y'all realize this, but we can check our answer, right, by evaluating f of f of 2, right? So when we plug in 2 here, our answer that we get back out is 25. That, right, my friends, is the remainder theorem right there at work. Boom. Right? So our remainder is the same thing as when we take our divisor or whatever, plug it into the original function, get the answer out. All right. Fun little tidbit. Would you guys like to try one? You want to try another one? All right, here we go. Try that out. While you guys are working on that, just want to ask y'all something. Did anybody try the Saturday tutoring? No? All right. Just wondering how it went, if anybody tried it. Yeah. Remember, it's online, it's not in person. It's another thing, right? But tomorrow, tutoring is open. If you guys want to go, 1 to 6. I understand that there's so few tutoring hours available. So if you guys ever want to go to tutoring and like then come in, like I won't like hold it against you if you come in a few minutes late, because I understand you have to walk across campus and all of that. Um,
Assignments to competition. Become divided. Without that be x minus 3.
Perfect. That's it. X minus 3. Yeah. Well, no, X plus 3. You're right. X plus 3.
As opposed to
Yeah. Add the 3 to the other side, and then you go. Yeah, that's all. Yeah. 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 I'm gonna try my best to post this homework tonight. If I don't get a chance to post it tonight, I'll post it tomorrow. All right. Again, this is on exam 2. All right. By the way, how's the videos for the class or mine I'm asking about, not other people's? Are they good? Yeah.
You got that one set up and now we were.
Yeah. It just takes me time to post it. That's the only issue. You know? Like, nah. I don't even know how to edit it. Oh my God, if I could edit it, y'all.
You.
Mhm.
Program.
Mhm.
Upload the video to the program.
That's what I need, man. Matter of fact, let me ask Copilot.
Should be a Microsoft phone.
Yeah. True. Wow. I had no idea. Okay. YouTube Shorts pending. Now for if I now if I was to edit these, I would be putting YouTube Shorts together, you know? I would still post like this though. I wouldn't change that. I would just put some short videos together, you know? All right, let's try this out real quick, all right? Again, I'm only using synthetic division because that's what they told us to use, you know, right? Do what y'all please. Mhm. So let's go. So I have -3. This is going to be 2. -3. 5, 4, 3. -9, 2. 8. And then I need 0 for 1. And then 2. Perfect, right? Let me just move that box real quick. There we go. All right. First things first, bring down that 2. Now, -3 times 2, -6. Now, -3 plus -6, -9. Now, -3 times -9 is 27. Now, -9 plus 27 is what? Is 18. Good. Now, -3 times 18, what's that? -46. Okay. Now, 8 plus -46 is, what is that? Is it 46? I don't know. I'm just taking y'all word for it. I don't know. It's 54? Let me see. I'm not even gonna lie. I don't even know. It's 3 times 18. Let me see what that is. Yep, -54. Oh, what's happening? -54. Now, 8 plus -54 is what? -46. Okay, that sounds better. Now, -3 times -46 is what? 138. Okay, I trust y'all. Now, 0 plus 138 is 138. Now, -3 times 138 is
14.
414. And now -414 plus 2 is
-412.
-412. Perfect. All right. So remainder. -412. All right. Questions on that?
Yeah.
You can plug it in if you want. It is. Yeah. You can just plug it in. Mhm. No. If you want to check if it's right, you could plug it in. Yeah. Any questions on this? All right.
Do you do it? For long division way?
Yeah, go ahead.
See.
So when you do the long division, you should have remainder 412, negative 412. As long as you got that same remainder, we on the same page. You good. Yeah. And if you want to check it, just take the -3, throw it into the function, find f of -3. Done.
But I think that,
It's not the exact answer. What went wrong?
but I don't know. See,
Let's see.
maybe I was wrong.
Nah, you might be right.
Because they give me negative 553.
Yeah, I got the 414. 556. When you plugged it in? I don't know. What depends? Like, you using your phone to plug it in? All right, which phone you have? You have Android or Apple? It's Apple. That's why. You can't do math with Apple. Yeah. Yeah, Android all the way. Yeah. Actually, you know what? Why y'all checking that? I want to look something up real quick, right? So I was in tutoring today, and I just found out this is gonna sound crazy, but it appears Google has a calculator. I want to see this. Yeah. Like like how Google has like Google Docs, Google Sheets, and all that. Yeah, so apparently there's a Google calculator, so I want to see this. Of course, when I Google it, I can't find it, but maybe y'all have luck with it. I don't know. What I'm seeing is, when you go on Google and then like you might type something in there, what's 5 + 4, and then it comes up. That's what I see, like in the browser, man. I don't know. I got excited. I thought that they had their own calculator or something like that. Mm. But if you guys are doing homework though, right? I like to share with y'all my favorite calculator. It's called Symbol Lab, right? SYMBOLAB, right? I really like this calculator because it it shows you step by step how to get the answer. It doesn't just go boom, oh, the answer's 5. It shows you step by step how to get the answer. I really like that. If you there is a pay version, but I forget what you get when you pay for it. It's something that you get for it. Mhm.
There's a few like online really sign cost center, computer cost center to calculate.
Yeah,
But they only let you use like certain features.
got you. Another one? Got you. Another one is called Desmos, DESMOS, right? Yeah, that's the graphing calculator. Yeah, that one's pretty nice too. Yeah. Yeah. It's good? All right, awesome. All right, let's move on. I feel like we get the idea of here, right? So here's what we're gonna be doing now, right? We're gonna be using the factor theorem to solve polynomial equations. We're building up to something big today. Something big today, all right? So using the factor theorem to solve a polynomial equation, the factor theorem is another theorem that helps us analyze polynomial equations. it tells us how the zeros of the polynomial are related to the factors, right? So recall the division algorithm, right? That we did earlier. F of x is equal to x minus k times q of x plus r. If k, right, is a zero, then the remainder r is f of k is equal to 0. And if f of x is equal to x minus k times q of x plus 0, or f of x is equal to x minus k times q of x, notice, right, written in the form x minus k is a factor of f of x, we can conclude, right, if k is a 0 of f of x, then x minus k is a factor of f of x, right? Similarly, if x minus k is a factor of f of x, then the remainder of the division algorithm, f of x is equal to x minus k times q of x plus r, is 0. This tells us that k is a 0, right? This pair of implications is the factor theorem, right? As we will soon see, a polynomial of degree n in the complex number system will have n zeros, right? That's important, right? So we can use the factor theorem to completely factor a polynomial into the product of n factors. Once the polynomial has been completely factored, right, we can easily determine the zeros of the polynomial, right? Yeah, so remember when we was in 28 and we did factor completely? Oh, we about to really factor completely, right? We was just playing around before. Now we about to really get it right now. All right. So we got the factor theorem. So according to the factor theorem, right? K is a 0 of f of x if and only if x minus k is a factor of f of x. All right. Here we go. Let me give y'all a little bit of tea real quick before we go any further. Give y'all the juice, right? So it's how to. So given a factor and a third degree polynomial, so it's a third power, right? We want to use the factor theorem to factor the polynomial, right? So first thing first, we're going to use synthetic division to divide the polynomial by x minus k, whatever that is. Then two, we want to confirm that the remainder is 0. If the remainder is 0, then that factor, yeah, that polynomial that we use, the x minus k, is a factor of the original. That's what it's trying to say, right? So write the polynomial as a product of x minus k and the quadratic quotient, right? If possible, factor the quadratic. Like go further, factor completely, right? Write the polynomial as a product of factors. So we're gonna have multiple factors being multiplied together to get back to that massive polynomial. That's what we're doing over here. Yeah. Things just got interesting right now. So there's no more, oh, this thing can't be factored. Yes, it can. Yes, it can. All right. So bam, here we go. Let's take a look. So using the factor theorem to solve a polynomial equation, show that x plus 2 is a factor of x cubed minus 6x squared minus x plus 30 using the remaining factors, right? Excuse me, find the remaining factors, excuse me. And then it says use the factors to determine the zeros of the polynomial. All right. Woo. Okay. Now, once again, y'all can use long division and do this if y'all want, right? If it was me, I'd use long division. But because they wanted it to use synthetic, I'm just following what they going through. So anyway, right? Let's start it off. X plus 2 equals 0. I'm gonna subtract 2. What I do to one side, I gotta do to the other. So I got x is equal to -2. Yay, right? So now I have -2. You already know. This is gonna be what? 1, -6, -1, 30, right? So what's first things first? Bring down that 1. Now, -2 times 1 is -2. Let's add these up. -6 plus -2, -8. -2 times -8, +16. -1 plus 16, what's that? 15. Now, -2 times 15, -30. And now 30 plus -30 is 0. Boom. Remained 0. So in fact, this is a factor, right? So by remainder 0, x plus 2 is a factor. Questions on this? You good? All right. So now that we found a factor, let's put that in parentheses. We found a factor. What's the quotient that we have here, right? So this original was what? X cubed. So we know that this is going to be x squared plus 15, right? Now we want to go a step further, factor that, right? I don't know about y'all, but I'm feeling tired. What's the factor? Just tell me. I know y'all can look at it and just tell me. What is it? X plus 2? No, X. Yeah. Of x squared minus 8x plus 15. What is that? Okay, I got you. I got you on the 5 and the 3, but give me the right signs. What is it? What is it?
Negative.
Negative and negative, right? Because -5 plus -3 is -8, right? And -5 times -3, +15, right? All right. So, real quick, our original question was x cubed. I forgot. X cubed minus 6x squared. One second. Minus x plus 30. Right? And I'm telling you that the factors for this is x minus 5, x minus 3, and this one up here, x plus 2. Right? That's our whole polynomial factored. Right? All right. Last but not least, right? They asked us to get the zeros of the function, right? What does that mean? That means literally take x minus 5, x minus 3, x plus 2, set it equal to 0, right? You already know what's going to come next, right? Set them equal to 0, x minus 5 equals 0, add 5, boom. X1 is equal to 5. X minus 3 equals 0, add 3, X2 is equal to 3. And then x plus 2 equals 0, subtract 2, subtract 2. So x3 is equal to -2. If you have these numbers jumbled, it don't matter. Like if your x1 was 3 and my x2 was negative, whatever. Doesn't matter, right? These are the answers right here. All right? Questions on this? So what we had to do here was we were given a polynomial, we were given a factor, and then we had to factor it completely. Then we had to just find the zeros of the function of this one, the x cubed minus 6x minus x. Yeah.
Okay, everything equal to zero.
So that's the zeros of the polynomial, this thing. Yeah. You're welcome. When we're graphing it, the zeros of the polynomial are where the graph will either touch or cross the x-axis. All right. Remember, if it's like multiplicity 2, or if it's even multiplicity, let me say that again, it's gonna bounce. But if it's an odd multiplicity, it'll go through the x-axis, right? So yeah, that's what that is. Good stuff, good stuff, good stuff. Do y'all want to try one? Or should we move on? Try one more? All right. Oh, shoot. So here's a scenario, right? I'm giving you this big polynomial. I'm giving you one of the factors. Prove that it's a factor. Then after you prove that it's a factor, I want you to factor whatever's remaining over. All right? Factor this completely. Then after that, tell me the zeros of the function. So find for me remainder 0. Then after that, whatever the quotient is, factor that more till there's nothing left. Then tell me the zeros of the function. All right, let's check this out. So start it off. I got x minus 2 equals 0. I'm going to add 2, add 2. So I have x is equal to 2, right? Gonna do that. See, I done messed up already. 2 on the outside, right? Boom. So now what do I have? I have 1, 4, -4, and -16, right? Bring down that 1 first. 2 times 1, 2. 4 plus 2, 6. 2 times 6, 12. -4 plus 12, 8. 2 times 8, 16. -16 plus 16, 0. Bam. Right? So that proves that x minus 2 is in fact a factor, right? So let me just write this down here so that when I scroll down, I'm not like forgetting nothing, right? So now what do I have left? I have x squared plus 6x plus 8. All right, I feel kind of tired. Just tell me what the answer is. It's going to be x plus 4, x plus 2. Perfect, right? Perfect, perfect, perfect. So originally I had x, what, cubed, what else? Plus 4x squared minus 4x, thank you, minus 16. And my factors are going to be x plus 4 times x plus 2 times x minus 2, right? What are the zeros? So I heard -4, -2, and 2. Perfect, 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 perfect. Very good. All right. Questions on this? Anybody? We good? All right, let's keep it moving. Because we didn't even get to the best part yet. Yeah, man. Yo, like this something big we building up to, man. Yeah, this about to be fire right here. Not this, but we got like right after this, we're gonna get something big. So we're gonna be using the rational zero theorem to find rational zeros. All right. So another use of the remainder theorem is to test whether a rational zero is a zero of a given polynomial. But first we need a pool of rational numbers to test. The rational zero theorem helps us to narrow down the numbers of possible rational zeros using the ratio of the factors of the constant term and the factors of the leading coefficient of the polynomial, right? Constant term, I meant to say, sorry. So consider a quadratic function with two zeros, x equals 2 over 5 and x equals 3 over 4. By the factor theorem, these zeros have factors associated with them. Let us set each factor equal to 0 and then construct the original quadratic function absent its stretching factor. So x minus 2 over 5 equals 0. Bop, bop, bop. Solve for, you're going to set equal to 0 and you want to solve for x basically, right? So we're going to add 2 over 5. Yeah. Well, basically just multiply everything by 5, right? So you have 5x minus 2 equals 0. Multiply everything by 4 for the other one. You have 4x minus 3 is equal to 0. Those are your factors, 5x minus 2, 4x minus 3, right? If we distribute it out, right, it comes back to the original function. No surprise there, right? So notice that the two factors of the constant term 6 are the two numbers from the original rational roots, 2 and 3. Similarly, two of the factors from the leading coefficient, 20, are the two denominators from the original rational roots, 5 and 4. All right? Just an instant, interesting observation. All right? Basically, that's all this is. Yeah. So we can infer that the numerators of the rational roots will always be factors of the constant term, and the denominators will be factors of the leading coefficient, right? This is in essence the rational zero theorem. It is a means to give us a pool of possible rational zeros, right? Okay. So that's our goal. So here's the theorem right here. Here's the theorem. Rational zero theorem right here, right? So the rational zero theorem states that if a polynomial, which is equal to f of x equal to an x to the n plus an minus 1 x to the n minus 1 plus all the way down to a1 to times x plus a to the 0, has an integer coefficient and an does not equal 0, then every rational zero of f of x has the form p over q, where p is a factor of the constant term, right? Which is a naught, and q is a factor of the leading coefficient, right? So when the leading coefficient is 1, the possible rational zeros are the factors of the constant term, right? So constant term over the leading coefficient. That's what it's trying to say. All right. This right here is fire. This will save you so much time, so much work if you do this trick. All right. So given a polynomial function, this is the t right here. Given a polynomial function f of x, you want to use the rational zero theorem to find rational zeros. So step 1, determine all the factors of the constant term, right? And all the factors of the leading term, right? Step 2, determine all the possible values of p over q, where p is the factor of the constant term and q is the factor of the leading coefficient. Be sure to include both the positive and negative candidates as well, right? Step 3, determine which possible zeros are actual zeros by evaluating each case of f of p over q. Long story short, use a division to make sure that they are actual factors. That's it. All right. Now, in the interest of time, for this example, right, we're just going to list all the possible rational zeros, right? We're not going to actually like find them, but let's list them, right? So remember, they're all going to be what? P over Q, right? And now P is all of the constant terms, right? So give me all of the factors of the constant term. What are the factors of the constant term? You know what? Let me use some colors. Let me use some colors because this might make it a little bit easier, right? This is P and this is Q. All right? Now, I want all of the factors of the constant term, -4. So what are the factors of -4? 2, 1, and 4, right? So I have plus or minus 1, plus or minus 2, and plus or minus 4. Technically speaking, there's another 2 there, but y'all get the idea, right? Over, what are all the factors of 2? 1 and 2. So I have plus or minus 1, and I have plus or minus 2, right? Now I'm going to list out all of the factors, right? I'll do them in pink, right? So, no, let me do it in black, right? So first off, right, let's start with the negatives, right? So we're gonna have, let's say, I'm gonna do the first term in the denominator, 1, right? So I have -1, I have -2, and I have -4, right? What else do I have, right? I have +1, +2, +4. Let's do the other number that's in the denominator, the 2, right? So I have what? I have -1/2. I have -2/2, but -2/2 is the same thing as -1. I have that already, right? So how about -4/2? But -4/2 is just -2. I have that already, right? Boom. So now let's start with the positives, right? So I'm gonna have what? +1/2, right? How about +2/2? But I have that already. That's +1. How about +4/2? I have that already. That's 2. These right here, all of them, are the possible zeros to this polynomial right here. 1/4 is not there because 4 is not in the denominator. Yeah. Oh, 4/1. Yeah, but I already have that 4/1. Yeah. 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 So all of these numbers that I found right here, right? They contain the factors for that polynomial, right? I don't know what they are, but I'm telling you that 1, 2, 4 of them, up to 4 of them will be the factors for that polynomial. All right. It's possible that the polynomial may contain complex factors within it, right? But I'm telling you, for all of the rational roots, the rational factors for this polynomial, this is it. These are all the possible ones. But how can we find out which one it is? You use a division. You prove that it has remained a 0. Once it has remained a 0, that is a factor, right? Let's see. Exactly, right? Now it sounds like a lot, right? But look what I did. I narrowed it down to just these numbers that you're plugging in, right? Otherwise, I could have had you guessing any number, you know? Yeah.
That's why the
Right.
it has to be
Mhm.
factors of the first and last provision.
Exactly, exactly, right? Yeah. To check if they are the actual factors of the polynomial, right? So how do you do that? You use a division, synthetic division, long division, whatever, right? When you get remainder 0, you found a factor. Yeah, right. Or actually, all of these numbers are x equal these numbers. So to find if you were using long division, just solve for 0, right? Or synthetic, this would be the outside number to prove it. Yeah. Go ahead. The P, the P comes from the constant term. So you see how we have -4, right? So all of the factors of -4. So you have 1, 4, and 2, right? Now the Q on the bottom is all of the factors of the leading coefficient. So in this case, it's 2, so that's just 1 and 2. Right? Yeah. The leading coefficient, the term that has the highest power, the number that's in front of it, right? That coefficient, I want all the factors of 2. So there's gonna be positive and negative 1 and 2. That's the only two numbers that multiply to give you 2. So now that you have those you have those numbers on top and bottom, you're gonna put them together to make all these numbers here. Yeah. So the numerator is from the constant term, and the denominator is from the leading coefficient term. Yeah. So these are all the possible zeros, and to prove if which ones are the actual zeros, you use the long division or the synthetic division to prove it. But you won't get 0. Well, no, you would get 0. Remain as 0. You're right. Yes, you can just plug them in and see which one will give you 0 to. Yeah.
These are all possible numbers.
They are. These are all the possible zeros, all the possible rational zeros. Let me be clear, right? Because sometimes you can have complex numbers in this, right? Complex roots as well.
Okay. So all of these somewhere of coordinates on this graph,
Exactly.
and which one give us 0?
Right.
And then,
Exactly. So that's another way to do it. No, we're not done. Yeah.
That's all.
Yeah. That is what it is. That is what it is. There's a way not to guess with this, right? So for those of you that have a graphing calculator or your calculator, or you have a table, right? You could actually type in this something. You can actually type in this polynomial, right? Use your table function, and you can see where some of the zeros are, right? This to the 4th power. If I find if all I need is like 2 zeros and I have a quadratic, once I have a quadratic, you already know quadratic formula, completing the square, done, right? So that's simple stuff right there, right? Sorry, let me just do 2 more things and we could call it, right? All right, so finding the zeros of a polynomial function, right? It's the same thing. That was an expression. Now I'm talking about a function, right? The rational zero theorem, right, helps us to narrow down the list of possible rational zeros for a polynomial function. Once we have done this, we can use synthetic division repeatedly to determine all the zeros of the polynomial function, right? Let me give you guys a little bit of tea real quick before we jump into anything. Even though you guys have pretty much seen the whole process right here. Sorry. Boy. All right, sorry about that, right? So given a polynomial function f, use synthetic division to find its zeros, right? So step 1 is to use a rational zero theorem to list all the possible rational zeros of the function. That's what we just did. Step 2 would be to use synthetic division to evaluate the given possible zeros by synthetically dividing the candidate into the polynomial. If the remainder is 0, the candidate is a 0. If the remainder is not 0, discard that candidate. Go on to the next one, right? Repeat the steps, right? Repeat step 2 using the quotient, right? Found with synthetic division. If possible, continue until the quotient is a quadratic. Once the quotient is a quadratic, you already know, right? Quadratic formula, complete the square, we done, right? Find the zeros of the quadratic function. 2 possible methods for solving the quadratics are factoring and using the quadratic formula, right? Forget that. Quadratic formula, completing the square. Keep your life simple, all right? Factoring can be challenging sometimes, all right? All right, let me get to the big shebang, like the big surprise I wanted to get to today. All right. Even though I've been hinting at it, I've been hinting at it, I've been hinting at it. So we're gonna just put a name on it right now. This right here, right here. We're gonna be using the fundamental theorem of algebra, right? Every math class that you take is always a fundamental theorem with it. There's a fundamental theorem of arithmetic. Now we're talking about the fundamental theorem of algebra, right? When y'all get to calculus, y'all will study the fundamental theorem of calculus. Nice, right? So let's talk about the fundamental theorem of algebra right now, right? So now that we can find rational zeros for a polynomial function, we will look at a theorem that discusses the number of complex zeros of a polynomial function. The fundamental theorem of algebra tells us that every polynomial function has at least one complex zero. So this theorem forms a foundation for solving polynomial equations, right? So long story short, any polynomial I give you can be factored, period. That's the fundamental theorem right there, right? So suppose f is a polynomial function of degree 4 and f of x is equal to 0. The fundamental theorem of algebra states that there is at least one complex solution. Let's call it C1. By the factor theorem, we can write f of x as a product of x minus c1 and the polynomial quotient, right? Since x minus c1 is linear, the polynomial quotient will be of degree 3. Now we apply the fundamental theorem of algebra to the third degree polynomial quotient. It will have at least one complex zero, call it C2. So we can write the polynomial quotient as a product of x minus c1 and a new polynomial quotient of degree 2, right? Continue to apply the fundamental theorem of algebra until all the zeros are found. So there will be 4 of them, and each one will yield a factor of f of x, right? I'm telling you, this is fire, right? This is the big deal right here. Yeah. Taking it up a notch right here. All right, here we go. So the fundamental theorem of algebra states that if f of x is a polynomial of degree n greater than 0, right, then f of x has at least one complex zero, right? We can use this theorem to argue that if f of x is a polynomial of degree n greater than 0, and a is a non-zero real number, then f of x has exactly n linear factors, right? So whatever function I give you, f of x, can be factored into a times x minus c1 times x minus c2 all the way to x minus cn, right? Where c1, c2, all the way to cn are complex numbers, right? Therefore, f of x has n roots if we allow for multiplicities, right? This is dope right here. This is dope.
Right.
Polynomial. Every polynomial can be factored. That's what it's trying to say. All right. So now, I know someone got a burning question right here. Here go the question right here. All right. Does every polynomial have at least one imaginary zero? All right. No. A complex number is not necessarily imaginary. Real numbers are also complex numbers, right? So you remember, complex numbers are of the form a plus bi, right? But if it doesn't have an imaginary component, right, all that means is that b is equal to 0, right? It's still complex. It's just a plus 0i, right? So that's what that's saying. I think this is the dopest thing ever, right? So one last thing, all right? So last thing, right? Using linearization factorization theorem to find polynomials with given zeros, right? So a vital implication of the fundamental theorem of algebra right, as we stated above, is that a polynomial function of degree n will have n zeros in the set of complex numbers. If we allow for multiplicities, this means that we can factor a polynomial function into n factors. The linear factorization theorem tells us that a polynomial function will have the same number of factors as its degree, right? So that's really important right there. And that each factor will be of the form x minus c, where c is a complex number. So let f be a polynomial function, right, with real coefficients. And suppose that a plus bi, where b does not equal 0, is a 0 of f of x. Then by the factor theorem, x minus a plus bi is a factor of f of x. For f to have real coefficients, x minus a minus bi must also be a factor of f of x, right? This is true because any factor other than x minus a minus bi, when multiplied by x minus a plus a bi, will leave imaginary components in the product. Only multiplication with conjugate pairs will eliminate the imaginary parts and result in real coefficients. In other words, if a polynomial function f with real coefficients has a complex 0, a plus bi, then the complex conjugate a minus bi must also be a 0 of the f of x, right? This is called complex conjugate theorem, all right? I'm throwing a lot of vocabulary at y'all, but you guys know the process to do this already. It's the same process that we said before. Once you get down to the quadratic formula, complete the square, boom. That's what this is. All right. So let's look at the complex conjugate theorem definition real quick. All right. So according to the linear factorization theorem, a polynomial function will have the same number of factors as its degree. And each factor will be of the form x minus c, where c is a complex number. If the polynomial function f has real coefficients and a complex 0 in the form a plus bi, then the complex conjugate of the 0, a minus bi, is also a 0. All right. So when you have like function graphs, excuse me, where the curve for some reason just like bounces off of something in the air, it's not off the x-axis, just in the air or whatever, that's the complex numbers right there. Right? That's the complex numbers working. Yeah. All right. Let me give y'all a little bit of tea real quick. All right. So given the zeros of a polynomial function f and a point c, comma, f of c on the graph of f, use the linear factorization theorem to find the polynomial function. So use the zeros to construct the linear factors of the polynomial. Multiply the linear factors to expand the polynomial, and substitute f of c into the function to determine the leading coefficient, and then simplify. All right. So basically what's happening in this kind of problem, you're going to be given some factors, right? But it's not complete, right? There's some a missing there. You have to use the point that they're telling you is on the graph to figure out what the a term would be, for example. And that's it. Not too bad. Not too bad.
Yeah,
All right, we could take a look at a question. All right. We'll call it our last question, then we'll call it a night after that, all right? All right, so using the linear factorization theorem to find a polynomial with given zeros, right? So the question here is asking us to find a fourth degree polynomial, so x to the fourth power, whatever, right? With real coefficients, -3, 2, I, such that f of -2 is equal to 100, right? So what do I know? What do I know right now, right? I have a 0 at -3. So I know that what? X plus 3, that's a factor. right? I have a 0 at 2, so I know that x minus 2, that's a factor. And I have a 0 at I, right? So what's that one going to be? X minus I. Okay, I'll take it. X minus I, all right? I was going to say really x minus 0 minus I, but whatever. It's the same thing, right? Boom. All right. But what do I know? I know that f of negative 2 has to equal 100, right? So what we could do, distribute these out. Let's get our polynomial going, right? And then we'll see what we could do from there, right? But also, I wanna say another thing too. From the linear factorization theorem, right? We know that this is going to be a polynomial that doesn't have complex like numbers inside of it, right? So that means that the conjugate x plus I must also be a factor as well. All right? That's what it was stating before. Now you already know the distribute, all that good stuff, right? So what I'm telling you is that there's going to be some function f of x is going to be equal to a times whatever this is, x plus 3, x minus 2, x minus x minus I, sorry about that, and then x plus I, right? So now we just got to figure out that a, right? And then we're good to go. We're off to the races, right? And we'll figure out our full answer. One way we could do this, right, without killing ourselves going through it, right? We know that f of negative 2 is equal to 100, right? So let me not even say that. 100 should be equal to a times negative 2. Hold on, I messed this up already. Plus 3, negative 2, minus 2, negative 2 minus I, negative 2 plus I, right? Let's put this all together, see what happens, right? 100 equals a times what's that? That's like positive 1, right? What's that? Like negative 4? And then we're just going to keep these here. Minus I, negative 2 plus I. I can tell you that those last two, we're going to have to distribute, combine like terms, foil it. We're going to have to foil it, right? So I have 100 is equal to, I'm just going to call this negative 4i, right? And then let's foil this last part. Negative 2 minus I, negative 2 plus I, all right? So foiling it, 100 is equal to negative 4a. This is going to be what? Plus 4 minus 2i, right? Plus 2i, and then minus I squared. Somebody help me. What's I squared again?
Negative 1.
Negative 1. Very good, right? Don't worry, it's on your formula sheet. All right. So this is going to be what? 4. This cancels out. Plus 1. Perfect, right? Because I squared we said was negative 1. Okay. 4 plus 1. I'm sorry?
No, they already have mine.
Because there's a negative there already. Yeah. So negative 4a times 5, right? Combine those up. What is this? 100 equals negative 20a, right? Divide by negative 20, divide by negative 20, kill the zeros. That's negative 5, right? So negative 5 is equal to a, right? Bam, right? So let's come all the way back up here, right? This is going to be, I'm just going to write it right here in the interest of time, right? This is 5 times x plus 3 times x minus 2 times x minus I times x plus I, right? This is not the final answer. You know, you need to distribute, combine like term, that's over. But because of time, I know y'all know how to distribute, so I'm just gonna call it at that, right? So boom. Yeah. Distribute the x plus 3 times the x minus 2, like multiply those out, right? Multiply out the x minus I, x plus I, multiply that out. Distribute the 5 at the end, huh?
Yeah, mine is down, negative down.
Negative down? What do
Yeah.
you mean? What do you mean?
Now we.
Okay.
Divide by -5, yes, it's fine.
Well, we found what A is. A is for -5.
Yeah. you
So-
put five, just 5, no -5.
Oh, it's -5. Good point. Good point. My fault.
So basically distribute.
Yeah.
Or distribute.
Distribute it so that I want a polynomial. I want 5 times x to the 4th power, -5 times x to the 4th power, you know? Right. Go down? Up, okay. Yeah. So that would be the final answer. You're welcome. I just know the time is going, so that's why I'm not doing that out, but remember this, distribute it out. I asked you for a polynomial, didn't ask you for factors, right? All right. So that's it. Have a good night, y'all.
But,
Bye, everybody that's on the recording.
but
All right. Hold on one second.
for the exam, or